Right, guys. Okay, let's get started.
Are you able to record the lecture?
Sorry?
Are you able to record the lecture?
I think somebody started, right?
Yeah, but then it stopped. And
Oh, did it? Okay.
yeah,
Okay.
thank you,
let me
sir.
Okay. Give me a minute, let me check. Okay. Right. Okay, can everyone hear me? Kwanit, raise your hand, right? Do you have any specific question?
Oh, no, sorry.
Okay.
Sorry, Professor.
Yeah, no worries. Okay, okay. I think someone left the mic on. Can you switch off your mic? Okay, thank you. Right, I think let's get started. Okay, just a quick recap on what we talked about last lecture. So we basically discussed how we can actually calculate the value of N naught and P naught. And these are the concentration of electrons and holes in the conduction and valence band respectively. And we mentioned that to sort of theoretically derive expression for N naught and P naught, we need two information, right? The first is your Fermi Dirac distribution function, which tells us what's the probability of finding electron at a particular energy level. And the other quantity that we need is the density of states, okay, G of E. And this density of state essentially tells us how many states you have at a particular energy level, right, per unit volume in a semiconductor. So in terms of the Fermi Dirac distribution function, okay, we mentioned that it's given by this expression here, which is a reciprocal function of 1 plus exponential E minus EF over kBT. And we briefly discussed the property of this function, right? We see that at 0 Kelvin, the Fermi Dirac distribution function is essentially a step function, right? Where below the Fermi level, the probability of finding electrons at those energy levels are essentially 100%, okay, or a value of 1. Okay, so it's 100% that you'll find an electron there. On the other hand, at energy levels above EF, okay, you will not find any electrons there, so the probability that you get is 0. Okay, and if you now have some temperature to the system, okay, the electron system, then you find that the Fermi Dirac distribution function basically starts to take on a sort of a gradual change in gradient. At EF, okay, it's no longer a step function, right? It's actually a gradual change in the probability now, where near to the EF value, okay, the probability of finding electron there is no longer 100%. Okay, that's for energy below EF. And for energy above EF, okay, the probability is no longer 0 as well, right? There's some finite chance that you'll find electron there. So this basically corresponds to the physical system that you expect, right? Because at some non-zero Kelvin temperature, electrons would some electrons would actually gain energy and they start to move up to the higher energy levels. Okay, that's why above EF, the probability of finding electron there is no longer 0 at 0 Kelvin. Okay, and in fact, if we increase the temperature, then you find that the near the interface of EF, right, the gradient of the function there becomes more gradual. Okay, and this corresponds to more electrons being able to move up above EF to take out the empty states there. All right. The other quantity which we need to know, the density of state, it's basically kind of inferred from the density of state for free electrons or free carriers. Okay, so we say that we can use the expression that we derive for free carriers or free electrons simply because in the case of free carriers, the relation between the energy and momentum is parabolic. And in the case of semiconductor near to the conduction and the valence band edge, the EK relation is also parabolic. Okay, so we can actually make use of the same expression. Of course, we have to modify some of the parameters to reflect the situation in semiconductor. Okay, but in terms of the general relation, it's the same as that of free carriers. Okay, mainly because of the similarity in the EK relation. Okay, so if we do that, then we find that the density of state in the conduction band is a root E relation. Okay, and similarly for the valence band, you also get a similar root E relation. And of course, in between the conduction and the valence band edge in the band gap, the density of state there is 0. This is obvious, right? Because in the band gap, there is no state that is present. Okay, so the states there is actually 0. Now with these two quantity that you have, you can then go on and derive an expression for N naught in the conduction band, which is the product of the density of state with the probability of finding electrons at this different energy levels or energy states, right? And if you want to find the total number of electrons, you will basically integrate the product of that two function, right, which is this area under the curve here, right, this lump that you see there, and the total area under this curve gives you the electron concentration in the semiconductor, okay, that's free to move. Okay, and based on the derivation, we get this NC exponential EC minus EF over KBT. There's a negative there, and this tells us, or rather this gives us a mean to calculate the concentration of electrons in the conduction band. And similarly, in the valence band, we multiply the density of state in the valence band with the probability of not finding electrons at those energy levels, and that will be 1 minus f of E. Okay, and the product of that two function gives us kind of like a similar expression, okay, which is this other lump that you see below the valence band edge. And if you integrate this function, okay, similarly we get an expression for the whole concentration. Okay, so we find that the form of it is quite similar, right, except for the NCMV and the term inside your exponential function. Okay, in the case of valence band, it's EF minus EV. Now take note that in deriving these two expressions, there is actually this assumption that was made, which is that your Fermi level must be sufficiently far away from the conduction and the valence band edge. Okay, if this condition is true, then these two expressions will be valid. Okay, and we also mentioned that what do you consider as sufficiently far away from the edges, right? We say that if the Fermi level is at least 3 kBT away from the conduction or the valence band edge, then that's treated as satisfying the condition. Okay, so if you need to check to see whether this equation is can be used or not, then you can use kBT as a reference amount, okay, to see whether it satisfies the condition or not. All right. So we apply this to, in fact, intrinsic semiconductor material, because we say that the N naught and P naught expression was derived without making any assumption to the type of semiconductor material that you're dealing with. Okay, so if we look at an intrinsic semiconductor material, a pure semiconductor, where number of electrons and number of holes must be equal. okay, because the mechanism that produce them is complementary, right? Electron goes out the conduction band, leaving behind a vacancy, which is essentially the hole in the semiconductor. Okay, so for every electrons that is created, you get actually a hole as well. So Ni and Pi are essentially equal. If you apply the expression that we have derived, right, to the pure semiconductor, we can write another set of equation for intrinsic semiconductor material, okay, where we replace the N0 with Ni and EF with EI. So EI here refers to the intrinsic Fermi level of the semiconductor. Okay, so similarly, you get another expression for Pi, okay, and we can make use of this expression to actually find out an expression for Ni in terms of the band gap. Okay, that's by equating, multiplying Ni and Pi together, right? If you multiply the two and you simplify it, you find that your intrinsic Fermi level actually cancel out in the exponential term, leaving behind a Eg term there. Okay, and that allows you to express Ni in terms of Eg. So really what this is telling us is that the intrinsic carrier concentration in the semiconductor is determined by two factors, right? One is the band gap of the semiconductor, and the other is the temperature at which the semiconductor is in. Okay, just dependent on these two terms. And in fact, we also see that using this equation, we can carry out measurements to determine how the Ni changes with temperature, right? And by expressing this as a straight line equation, okay, the graph can be used to determine the band gap of the semiconductor. So these three graphs that is shown here for different materials basically illustrates the kind of straight line equation that you get. For a semiconductor like silicon, right, you get the straight line with a certain gradient. For a larger band gap semiconductor like gallium arsenide, you expect the gradient to be steeper, right, the magnitude to be larger because the band gap of gallium arsenide is larger. And germanium, having a smaller band gap, will have a more gentle straight line equation. Okay, so this is something that you can do, right, in terms of measurement to find out what's the band gap of a semiconductor. Now, by equating Ni to Pi, we can actually derive an expression for the intrinsic Fermi level EI, okay, where after simplification, you find that it can be expressed as the sum of two terms, right? The first is the middle of the band gap, E mid, and the second term is a function that depends on the natural log of the ratio of the effective masses, okay? And in fact, this second term here is generally quite small, which means that the intrinsic Fermi level is approximately in the middle of the band gap. Okay, as illustrated in this figure here, right? If you draw the E mid and the EI, okay, the two are actually quite close together. So in most cases, if let's say you are not required to find out the difference between E mid and EI, you can just assume that the second term is approximately 0, right? And just treat EI as E mid. Okay, for most calculation, that's the assumption that you can make. Unless, of course, the question requires you to work out the difference between E mid and EI. Then you have to make use of this second term here and work out the actual value. Now, another thing that we can also derive is you find that when you multiply N0 with P0, it is actually exactly the same as Ni multiplied by Pi. And because Ni and Pi are the same, we can write this as Ni square. This actually gives us a very useful expression that we can use to relate N0 to P0 if you know Ni value, right? Okay, this expression here is called the mass action law. Okay, in today's discussion, in fact, we'll see that we make use of this to do some calculation for N0 and P0. Okay, so in terms of the N0 and P0 expression, other than expressing them in terms of the effective density of states, we can also express N0 and P0 in terms of Ni. Okay, if you do that, then you find that the term in your exponential function is now in terms of EF and EI. Okay, so it's no longer respect to EC and EV. So this is in fact another complementary set of equation that you can use to calculate N0, P0, or EF, depending on what you have. Okay, so this is essentially the same as the first set of equation that we have, right? Depending on what you have, you choose the suitable one to use. Now for today's discussion, we are going to see how we can apply some of this equation that we have derived to calculate electron and hole concentration in extrinsic semiconductor material, okay? And we discussed in previous chapters that in extrinsic semiconductor, okay, we basically realize the electron and hole concentration through doping the semiconductor with impurity atoms. Okay, we put in atoms that is from different group, okay, to achieve an increase in electron or an increase in the hole concentrations in the semiconductor. So for a start, okay, let's look at N-type semiconductor where donor impurity atoms are put into the semiconductor, okay, and we use this as a starting point to see how we can actually work out N0 and P0 without having to know the Fermi level in the first place, right? Because if you know the Fermi level, you can just use the previous sets of equation and find out N0 and P0, right? If you know the actual value of EF. Now in the situation where you do not know what is EF, then how do we calculate N0 and P0? Okay, so that's what we're trying to answer here. Now, so in terms of the N-type semiconductor, right, we see that there is actually this charge neutrality equation. For N-type semiconductor, your N0 is given by the sum of donor doping concentration, ND, plus P0, the minority carrier concentration, okay? So this comes about because of conservation of charge in the semiconductor. So with this one equation, if let's say the ND value is known, then basically here we're trying to find out what is N0 and P0, okay? So one equation, two, one equation, two unknowns, you basically need another equation to solve this, right? To find out N0 and P0. So remember, you know, other than this charge neutrality equation, an equation that relates N0 and P0 is actually the mass action law, the N0 P0 equals to Ni square. This in fact gives us another set of equation that we can use, okay, together with the charge neutrality, two unknowns, assuming that you know Ni, and two equations, we can actually solve this simultaneously, right? So if you, in this case, replace the P0 in the charge neutrality equation with the expression from mass action law, we get N0 equals to ND plus Ni square over N0. Okay, so over here, if you multiply both sides by N0, then you basically get a quadratic equation in N0, right? This is N0 square minus ND N0 minus Ni square. So assuming that ND and Ni are known values, then this is simply just a quadratic equation, right? Where it's in the form of ax square plus bx and plus c, okay, where the c is the Ni square, right? Okay, so these are constants, right? It's a quadratic equation. And if you solve this, there's a formula we can use, right, for quadratic equation. If you apply this and solve the N0, you basically get minus b plus minus square root b squared minus 4ac over 2a. If you apply that, we get this form here, right? Nd plus minus square root nd square plus 4ni square over 2. And if you look at the two possible solutions, right, one is nd plus square root nd square plus 4ni square over 2. The other is the negative one, nd minus. The nd minus, in fact, will give you a negative value. Because if you look at the square root term here, right, okay, this square root term will give you something that is going to be more than nd, okay, because you have an extra 4ni squared there. So this would increase the value to above nd square. If you take a square root, you're going to get something that's more than nd. If you subtract that away from nd, the n naught actually become negative. Okay, so negative electron concentration, that's something that is, it's not sort of not feasible, right? Because you don't have negative particles. So we can omit the negative solution, and that leaves us the positive ones. Okay, and this positive solution is the n naught value, the majority carrier concentration. Now, in fact, if your doping concentration is much greater than intrinsic carrier concentration, right? If your ND is much greater than Ni, then you would find that the second term in your square root term becomes negligible. And if you take a square root and you add it up, it's just 2nd over 2, which is just equals to nd. Okay, so when your doping is sufficiently large, the majority carrier concentration electron will be just equal to your doping in the semiconductor. Okay, so what that means is that depending on what is your doping, right? If you know that your doping is much greater than the intrinsic carrier concentration, you do not in fact need to apply this solution to do the calculation. Okay, you just need to write down n naught approximately equals to nd. That is provided that you know that your doping is sufficiently large. Okay, if the doping is actually not sufficiently larger than Ni, then you have to apply this solution here, okay, to work out the actual value. Okay, so if you know it's sufficiently large, then you do not need to use this equation. All right. And in fact, once you found the majority carrier concentration, to find the minority carrier concentration, you can just use the mass action law, right, to find out what's the P naught. Okay, and that will give you both N naught and P naught value. Okay, so in this case, we do not actually require the knowledge of EF. Okay, so with N naught and P naught, then you can put it back into the the expression that we have in the last discussion to find out what is the EF. Okay, so we can either use this that relates to the effective density of state, or we can use the other one that relates to intrinsic carrier concentration to find out what is the Fermi level. Okay, what is the position of the Fermi level? Okay, of course, which one to choose would depend on what value you have. Okay, if the question gives you the effective density of state, then you can just use this equation here, right? On the other hand, if you know the intrinsic carrier concentration, then you use this second expression here to find out where is your EF. Okay, these two are essentially the same. They're just expressed differently. And in fact, similarly, you can also use the P naught expression, right? Using the P naught value that you calculated to find out the Fermi level position. And the solution that you get should be the same, whether you use the N naught or the P naught expression to work out your Fermi level. Okay, because this is thermal equilibrium condition, the Fermi level is the same. Now this last part here, in fact, I think we discussed this previously, right? If you look at the N-type semiconductor, you find that the Fermi level is always above the intrinsic Fermi level. Okay, so it's always above, right? In fact, previously we also say that if you find the Fermi level below the intrinsic Fermi level, right, then this must mean that your semiconductor is a P-type semiconductor, right? If it's P-type, then you'll find the Fermi level below the intrinsic Fermi level. Okay, so from the graph itself or diagram itself, right, you can tell whether you're dealing with N-type or P-type by looking at the position of the Fermi level. Okay, let's look at an example to see how we can apply this. Okay, so in this example here, we have a silicon sample that is doped with phosphorus atoms. Okay, so if you recall, the phosphorus atom is a group 5 element, and a group 5 element will make the silicon crystal essentially N-type. Okay, so we make it N-type. And the doping concentration is 10 to the power 16 atoms per cubic centimeter. Intrinsic carrier concentration of silicon is 10 to the power 10. So if we compare this, right, the doping is actually 6 orders of magnitude larger than the intrinsic carrier concentration. Okay, so this 10 to the power 16 here is your ND, right? And this 10 to the power 10 is your Ni. So if you compare between these two, the ND is obviously much greater than Ni. Okay, so in this case, right? In this case, in fact, you do not need to use the equation. Okay, you do not need to use or rather the solution that we have derived, which is the solution of the quadratic equation, right? But nonetheless, even if you use it, it's fine. You know, you're still going to get just the ND value, 10 to the power 16. Okay, that's because your Ni is so small, right? It's a million times smaller, right? It doesn't make any difference, even if you add it. Okay, so in fact, you don't even need this step. You can just straight away say that because your donor doping is much greater than intrinsic carrier concentration, N naught is just approximately equals to ND. That's it, okay, which is 10 to the power 16. All right. So the thermal equilibrium minority carrier concentration, which is the whole, can then be calculated using the mass action law, where P naught is Ni squared over N naught. And that gives us 2.25 by 10 to the power 4 per cubic centimeter. Okay. So with the value of N naught and P naught, we can then use the either the N naught or P naught expression, doesn't matter which one you use, okay, to work out the position on the Fermi level. So in this case, we have chosen to use the N naught expression with related to Ni, because we know what is Ni. Okay, the effective mass in the conduction band is not given, so we use the Ni expression. And if you rearrange this, okay, with EF minus EI on the left, okay, then you can substitute in the values that you have calculated to find out where's the position of the Fermi level. Okay, so if you calculate this, you get 5.55 by 10 to the power minus 20 joules. And we can convert this to electron volt by dividing this value with 1.6 by 10 to the power minus 19 joules. And that gives us 0.347 EV. Okay, so EF minus EI is a positive value 0.347 EV. Okay, this means that EF must be above EI. Okay, so this is consistent with what you expect by putting in phosphorus atoms, okay, which is an N-type semiconductor. So EF is above EI. Okay. So in fact, you can also choose to use the value of P naught that you calculated with the P naught expression related to Ni. Okay, so we use that expression instead, and you put in the values of Pi that you calculated. You will expect to find, in this case, EI minus EF equals to negative 0.347 EV. Okay, if you multiply both sides by negative 1, right, then you get EF minus EI equals 0.347 EV, which is the same as what you get with using the N naught expression. Okay, so regardless of whether you use N naught or P naught expression, the position of the Fermi level that you get here must be the same, right? Okay, so if you draw the Venn diagram, then you have the Fermi level that is above the intrinsic by 0.347. So in the case of silicon, the band gap is 1.12. If you take half of that, okay, half this length here, or this distance, is 0.56 EV. So 0.347, it should be quite close to the conduction band edge. Okay. Now let's look at another example. Suppose we have a germanium sample and we dope with, again, donor impurity atoms. In this case, ND is 5 by 10 to the power 13 per cubic centimeter. the intrinsic carrier concentration of germanium is 2.4 by 10 to the power 13 per cubic centimeter. Calculate the thermal equilibrium majority and minority carrier concentration. So in this case, if you compare now the ND with NI, right, the difference is only like 2 times. Okay, the ND is only about twice that of NI. Okay, so this is not considered sufficiently large enough. Okay, and if that's the case, you cannot just write N naught equals to ND. Okay, in this case, we have to apply the expression, okay, the quadratic expression, and to find out what's the value for N naught. Okay, so I suppose a question that some of you might have is, what is considered sufficiently large enough that you can just approximate N naught to ND. So as a general rule, right, a sort of reference value, you can consider if it is at least more than 10 times that of the intrinsic, then we can treat it as sufficiently large, okay, at least 10 times. Of course, if you are not sure, then just use the solution here, right, which is also fine because this should give you the exact solution. Okay, anyway, if you apply that, you get an N naught of 5.97 by 10 to the power 13. So remember your donor doping is 5 by 10 to the power 13. Okay, so there's actually an extra 0.97 by 10 to the power 13, which will obviously come from the band-to-band generation, right? Because the doping you only put 5 by 10 to the power 13. So the extra 0.97 must come from the band-to-band generation. So why don't you see this for the previous case? Okay, simply because in the previous case, the donor doping is so large, right, that the contribution from band-to-band transition is very, very small. Okay, so it could be like, 5.00000000 some value, right, which is extremely small. And if you approximate it, it's just the doping that you put in. Okay, so in this case, because the doping is not high, you have to take into account the band-to-band transition. Okay, and that's why in terms of solution, you have to apply the quadratic solution to find out what's the actual concentration. So similarly, once you find out N naught, you minority hole concentration using mass action law, Ni square over N naught. And if you plug in those values, you get about 9.65 by 10 to the power 12. Okay, so this is how we can apply, the solution that we have obtained to calculate concentrations of electrons and holes. Fairly straightforward. Okay, just something for you to think about. If you have this n-type semiconductor where N naught is greater than P naught, right? And in the previous discussion, we say that first we make N naught the subject and replace the P naught with N naught, and then we get a quadratic equation in N naught. However, in this case, if let's say instead of doing that, we replace the N naught with P naught instead, and we get a quadratic equation in P naught, and you try to apply the formulas and the same approach to solve this, okay, would there be any problem, right? Okay, so I'm going to leave this as something for you to think about, and if you would like discuss in the class, feel free to raise it up when you go for tutorial class, and we can discuss it in class in terms of what is the implication of this. All right, so go and think about it. In this case where instead of using the majority carrier concentration variable, right, as the subject, we use P naught instead. How would that affect your calculation? Okay, think about this. So similarly, for the case of P-type semiconductor, right, we can actually carry out the same approach where using the charge neutrality equation for P-type semiconductor, in this case, you get P naught equals to Na plus N naught, right? And mass action law, in this case, we replace the N naught with P naught because the majority carrier is actually the holes. Then we actually also will get a quadratic equation in P naught. And applying the formula for quadratic equation, right, we get similarly the solution for P naught, which is of the form that is quite similar to the N naught. Okay, you have Na plus Na square plus 4Ni square over 2. Only difference is in terms of the doping that you use. Instead of ND, now you notice that this changes to NA. Okay. And obviously, once you have that, then you can find the minority carrier concentration using N0. Okay, and that allows you to determine both the electron and hole concentration in the semiconductor. So similarly, if your accepted doping is significantly greater than Ni, so as a guide, you can use 10 times, right, as a reference. So if it's at least 10 times or more, then you can treat it as very large, and we can actually approximate the P0 to NA. Okay, so the approach is really the same. And once you have the N0 P0 value, then you can use the P0 N0 expression in terms of MV or Ni to find out where's the position of the Fermi level. Okay, so the approach that we're taking here is essentially first find out the carrier concentration using charge neutrality equation and the mass action law. And once you find those values, you can then put in into the equation that relates to EF to find out the position of the Fermi level. Okay, so that kind of complete the whole calculation, right, where we can determine the Fermi level, we can determine the N0, we can determine the P0. Okay, so like I say, in the case of p-type semiconductor, similarly, if you use the minority carrier concentration expression, the EF value you get should be the same, right? Should be the same. If not, then you have to go back and recheck. Okay, thermal equilibrium, you expect their values to be the same for the Fermi level. Okay, so p-type semiconductor, like I mentioned before, the Fermi level is below the intrinsic Fermi level. And in fact, the closer you get to the valence band edge, the larger the hole concentration. All right. So just from a figure itself, if you see the Fermi level below the intrinsic, then it tells you that it's a p-type. Okay, that should be clear to you. So what we've discussed so far is essentially looking at just purely N-type or purely p-type semiconductor, right? Where you just dope a semiconductor with either a p-type or n-type dopants. However, in practical semiconductor, a lot of times you find that the semiconductor is having actually doping from both p and n-type. Okay, so this type of semiconductor that has both type of doping are called compensated semiconductor. And the reason why they are like that is kind of illustrated here. Typically if you want to make some, for example, a PN junction, right, in a semiconductor wafer. Typically, the semiconductor wafer could come pre-dope. Okay, so you could have, say, an N-type silicon wafer that is your starting material. If I want to dope part of it so that we make it into a PN junction, then we have to put boron atoms into that part of the semiconductor. Okay, so you see that there's this, this sort of blackish region there. That's basically can be in the form of like photoresist to block the boron atoms, okay, from the part that you don't want to dope. Okay, so you put photoresist like this. Only the part that's exposed to the boron atoms, right, will get into the semiconductor and make it p-type. Okay, so if you put sufficient amount, right, then you find at first the boron atom will basically cancel out the n-type doping. Okay, in the region that you are doping, and you convert it to intrinsic, and then the addition that you add will then convert it to p-type. Okay, and so this is kind of like the final doping you would get, if you dope it enough, and this gives you a PN junction diode, right? But of course, in this p-type material, it's not just solely doped by boron, because it initially have this background n-type doping as well. Okay, so in the p-type semiconductor, you find that there's actually both donor and acceptor doping. Okay, so the acceptor doping that goes in, right, first of all, will cancel out the n-type doping. Okay, once all are cancelled out, the addition that you add will turn it into p-type. Okay, so that's the idea behind this. And so in the case of compensated semiconductor, there is three possibilities you can get. Of course, the first is your, the n-type, which is when if you're to say dope both acceptor and donor, right? If your net donor is greater than the net acceptor doping, Okay, then after you cancel out, there's still balance of donor doping, right? So that will make the semiconductor N-type, okay, on average. And similarly, if your Na is greater than Nd, then your acceptor doping, the balanced one, after compensating from Nd, right, will make the semiconductor P-type. In fact, in the situation where your donor doping is exactly matching the acceptor doping, they cancel out exactly, and your semiconductor becomes intrinsic, okay, with both types of dopants in it that is the same. So you do get sort of a complex situation like this, right, where it's not just one type of doping anymore. There's actually multiple dopings, okay, that's put into the semiconductor. And in fact, in such a doping, remember with donor impurity or acceptor impurity atoms that's introduced, you actually get this extra energy levels in the donor level and this extra states at acceptor levels. Okay, and this actually makes the transition a little bit more complex than a pure semiconductor, right? Because if you recall, in a pure semiconductor, electrons and holes basically goes from valence to conduction band, right? Either it goes up or it comes down. With the presence of this donor and acceptor level, right, you actually have a few more transition possibility, right? You could have electrons going to the donor level, right? That's one possibility. And maybe electrons from donor to acceptor to donor level. And from donor level, it can also go to the conduction band. And in the recombination part, you can also have like multiple paths. Okay, you can have, for example, conduction to valence band. That's a direct transition. You can also have, perhaps electrons from the donor level going down to the acceptor level, and then maybe go down to the valence band. So there's now this additional levels that you could transit, right? So then the question is, how does this actually affect the equilibrium concentrations of electrons and holes in the semiconductor? Okay. So it turns out that in this case, right, we actually similarly use the charge neutrality equation for the compensated semiconductor, okay, where we say that the sum of positive charges is equal to the sum of negative charges. That's the charge neutrality equation. So if you actually have both types of doping, then your charge neutrality equation becomes P naught, which is the positive charge, right, the holes, plus the ionized donor dopants, right? Remember, for dopants like phosphorus atom, when it gives off the electron, the donor atom becomes positive charge. Okay, so this will contribute to all the positive charge that you see in the semiconductor. That's why it's added to P naught. On the other side, you have the negative charges, which are made up of the electrons and the ionized acceptor dopants. Okay, so these are the ones where it has an incomplete bond, right? And you have an electron from neighboring site coming to take the incomplete bond. The acceptor dopant now gain one more electron and it becomes a net negative charge to that. Okay, so it has a negative charge. So the total number of negative charges will be N0 plus Na. So the minus here basically indicates that it's the ionized acceptor doping, right? On the donor side, it's positive because it's referring to the ionized ones. Of course, if you assume the case where all the impurity atoms are actually ionized, then you can drop the plus and minus and just indicate it as Nd and Na, because all have ionized, so they'll be equivalent to Nd and Na. So in fact, this is the one equation that we have now relating P naught to N naught. And obviously, like previous cases, if you want to find out what is N naught and P naught, we can use the mass action law, right, to form this into a quadratic equation and then solve for the N naught or P naught. So of course, this charge neutrality equation here is like a general case. In fact, if you have only purely donor impurity atoms, that means your acceptor doping is 0, right? If you take this out, then you get back the charge neutrality equation for purely N-type dope, or purely N-type dope semiconductor, right? And if it is a purely P-type dope semiconductor, your Nd will be equal to 0, and that gives back the charge neutrality equation for a P-type semiconductor. Okay, so really, I would say that you don't even have to remember the one with an N-type or the one with a purely P-type semiconductor, you just use this general one. Okay, so remember this general one, then the others you can infer. Okay. So together with the mass action law, we can convert this expression to just N naught or P naught. So if you consider a case where the ND is much greater than NA, that means it's an N-type semiconductor, then we use mass action law to convert this equation into a quadratic equation in N naught. Okay, where now this dopant there is no longer just one dopant quantity, right? It's now two. It's the donor and the acceptor one, the difference between them. And if you solve the quadratic equation, okay, similar to previous consideration, you actually get the same form. The only difference is that the doping part is the net doping in the semiconductor. So it's ND minus NA. In the square root bracket, you also have ND minus NA. And similarly for P-type, okay, using the mass action law, and you solve this, right, together with, you apply the mass action law with the charge neutrality equation, you get a quadratic equation in P naught, and you apply the solution for quadratic equation, you get another similar expression there, okay, that tells you how to calculate P naught. Okay, so the approach is really the same, right? Just that in this case, you have to take into account both dopings due to this donor doping and acceptor doping in the semiconductor. Okay, just the difference between the two. So in fact, we look at these two solutions, right, for N and P type, you can actually generalize the solution, right, as such. You can say that the majority, okay, carrier concentration is simply equals to, right, the first term there is in fact just a net doping okay, that's a net doping plus square root. The term there is also considered net doping, right, because it's Na minus Nd or Nd minus Na, right? So it's net doping square plus 4 Ni square, and in the denominator is just over 2. Okay, so depending on whether it's N-type or P-type, the majority carriers will be the respective carrier type. And once you find this, then the minority carrier concentration, right, can be determined using the mass action law, which is Ni square over the majority concentration. Okay, so if you generalize the solution for N and P type, then that's the solution you're going to get. Okay, so you can choose to remember this solution form, or if not, right, if not, you can just derive it on the spot where you need it. Okay, so I would think it's quite straightforward to memorize, so typically I will actually memorize, but it's really up to you. Okay, if you don't memorize, you can also derive from scratch, right, because you understand where this comes from. Okay, so let's look at another example to see how we can apply this. You have a germanium crystal that has both donor and acceptor impurity atoms. So in this case, you notice that the donor impurity is 5.8 by 10 to the power 14. Acceptor is 5.4 by 10 to the power 14. So looking at this, obviously the donor is of a larger concentration, right? Which means that the semiconductor will become N-type. Okay, the net doping that you expect should be N-type. And we're supposed to calculate the electron and hole concentration. Okay, so this is an N-type compensated semiconductor material because you have both dopings and donor doping is greater than acceptor doping. So it's a compensated one, but it's N-type. Now, if you apply the solution of the quadratic equation to find out the majority carrier concentration, because in this case, right? You find the net doping, the difference between the two is 0.4 by 10 power of 14, compared to the intrinsic carrier concentration, which is 2.4 by 10 power 13. The difference of the net doping is only a little bit more than the intrinsic carrier concentration. It's not even 10 times, right? It's kind of not even 10 times. So we have to apply the formula for the solution of the quadratic equation, okay, which is net doping plus square root net doping square plus 4ni squared over 2. And you apply in those values, you get 5.12 by 10 to the power of 13. And with this, you can then work out the P naught using the mass action law, and that gives us 1.12 by 10 to the power of 13 per cubic centimeter. All right. Okay, so you see that in this case, using the charge neutrality equation and the mass action law, we can actually independently find out what's the N naught and P naught. And once you have this knowledge of N naught and P naught, you can put it back into the Fermi level expressions, right, to find out the position of the Fermi levels. Okay, anyone has any questions? Okay, if you have no question, let's go for a 10 minutes break. Okay, we'll come back in 10 minutes time and we'll continue the second half of the discussion. Okay, now the time now is 4:55. Okay, let's come back at 5:05 to do the rest. All right. Okay, let's get back to the discussion again. Right.
Sir, can you record this as well? Sorry.
Yeah, okay. Let me check. I thought it was recording just now.
I think you stopped it during the break.
Oh, did it?
Yeah.
Okay, let me check. Okay. Okay. Okay, for this second part of discussion, we're going to now move on to carrier transport. This essentially refers to the movement of carriers in the semiconductor, right? So in order for a semiconductor device to be useful, obviously you need the carriers to be moving, right, in a device application. So in semiconductor, there are actually two basic sort of movement mechanism, okay, which we call transport mechanism. There is first the drift, okay, which is movement due to presence of electric field. Okay, so when the charges like electrons and holes move due to presence of electric field, we call that motion a drift. Okay, the resulting current is called a drift current. The other mechanism is due to the diffusion effect. And as probably most of you all will know, right, when you talk about diffusion, it refers to the situation where there's a difference in concentrations in different parts of the semiconductor. Okay, this difference in concentration will result in the net flow of the charge, okay, in the direction from high to low concentration. Okay, so we call this a concentration gradient. So when the flow of charge occurs due to the concentration gradient, we call this a diffusion process. And the resulting current is called a diffusion current. All right. So, you know, when, strictly speaking, when you have this transport mechanism occurring in the semiconductor, right, where you get a net current flow, whether due to drift or diffusion or both, strictly speaking, you know, the semiconductor, it's not in equilibrium, okay, because the current is changing, right? But, you know, under thermal equilibrium condition, if the current flow is not so large that it disturbs the thermal equilibrium condition, then we can assume that, you know, the thermal equilibrium condition is still applicable. Okay, so that's the assumption that we can actually make if your current is not too large, okay? And also that your electric field do not produce extra carriers in the semiconductor. Okay, so, you know, a lot of times we make such assumption, right? Although strictly speaking, it's not thermal equilibrium condition anymore, you know, but approximately, right? Approximately, if the electric field doesn't produce extra carrier and the current doesn't change the concentration too much, we can still assume thermal equilibrium condition. Okay, so in fact, other than this drift and diffusion, there's actually another process that causes carrier to move, right, which is due to the thermal effects, okay? So wherever you have semiconductor that's at non-zero Kelvin temperature, the electrons and holes in the semiconductor can move, okay, or in general, particles can move when the temperature is not 0 Kelvin. And for those of y'all who have studied this kinetic theory of gases, right, you know that the thermal energy of particles in general in 3 dimensions has an energy of 3/2 kBT. Okay, the kB here is the Boltzmann constant, right? T is obviously the temperature. And in each direction, right, the thermal energy that's associated to it is half kBT. So in 3D, you have essentially 3 degrees of freedom. And so in total, you have 3/2 kBT. So in fact, if you consider one direction, right, where the thermal energy is half kBT, and if you apply this kinetic energy of particles, half mv squared, right, to 3 okay, this is 3D now. If you apply to 3D, 302 kBT, then we can find out a thermal velocity, okay, that's associated to a particle that's moving in 3D. Okay, so this is given by VTH equals to square root 3 kBT over m. Okay, so there's this thermal velocity that a particle would have, okay, that's moving in 3D, that's related to temperature, right, that it's in. And if you consider a temperature of, in fact, 300 Kelvin, okay, and if you consider electrons, okay, then you do that calculation, you actually get a velocity of about 10 to the power 5 meter per second. Okay, 10 to the 5 meter per second, that's the thermal velocity that electron will have at 300 Kelvin. Okay, we use the electron rest mass. Okay, so you could consider, for example, electron, free electrons. If they have a temperature of 300 Kelvin, then they are actually moving around quite fast. So that corresponds to about like 100 kilometer per second, right? And you convert it to kilometer per hour, right? That's actually 360,000 kilometer per hour, which is very, very fast. Look at, say, the bus that you take, right? What's the maximum speed that the bus is moving on the road? It's usually maybe 80, 90 kilometer per hour, right? That's the maximum. If you consider like aeroplane, right, that's flying, right? When if you take a plane and it's flying to the cruising height, it's cruising speed, right? What's the typical speed that the plane is flying? Everyone knows? Everyone noticed? Everyone know what's the cruising speed of aeroplane? Everyone noticed? Nobody knows? Nobody?
900 kilometers per hour.
900, yeah. So, okay, so we have taken airplane before, and you look at the screen, right, that shows you the position of the plane and the speed that's going. Typically it could be cruising at around about 1,000 kilometers per hour. Compared to electrons, you see that electrons is actually sort of zipping around at a speed of 360 times that of the speed at which the plane is cruising. So they're actually moving around very fast. Okay, then the question you may ask is, well, if they're actually moving so fast in a semiconductor, right, will you be having electrons actually zipping out of the semiconductor, right, and flying out all over the place? So obviously the answer to that will be no, because although the speed is very fast, right, if you were to look at the kinetic energy that's associated to that, it's actually only several hundred of electron volt. Okay, so it's just a fraction of electron volt, which is actually very small. To get out of the semiconductor, right, for electrons at the conduction band edge, to get it out, typically you need more than 4 electron volt. Okay, so the kinetic energy of this electron is actually so small that it's not enough to bring it up to vacuum level so that it can escape from the semiconductor. Okay, so although they seem to be moving quite fast, but the energy is low. And at the same time, these electrons in the semiconductor, they're also not moving in a straight line all the time, because as they move around randomly, right, they will knock into some atom, then they get kicked in a different direction. Then after a while, they may kick in a different direction. So if you observe how electrons move in a semiconductor, you actually see it bouncing around, in random directions. So there's actually no what we call directed motion, okay, which would cause a change in the charge in terms of its position, and in turn give rise to a current. Okay, the current, you need to have a net flow of charge through a position. Okay, so in the case of thermal energy, it doesn't give rise to any thermal current because the electron is zipping around and its average position is actually not changing, right? It's more or less at the same point. Okay, so thermal velocity, it's essentially, doesn't contribute to current because there's no directed motion. So as illustrated in this figure here on the left, okay, so if you observe, for example, a hole, right? Let's say you consider a hole in a semiconductor. So, suppose you have a hole at this position, and based on the thermal energy that this hole have, right, it could be sort of moving first in direction 1, Then after a while, it could knock into the lattice atoms. Then you get kicked into another direction 2, and 3, and 4, and so on. So if I have this random direction that is kicking around, overall it more or less bring it back to the same position. So it's sort of knocking around, but it's still more or less in the same position. So the charge actually doesn't have a net displacement. Okay, so current is not produced. To produce current, right? What we need to do is to apply an electric field in the semiconductor. So suppose you apply some electric field that points from left to right. So to the positive charge hole, okay, other than the thermal motion, right, which is indicated by this dashed line now, right, you find that the electric field introduces a horizontal displacement in the direction of electric field. Okay, so other than being kicked in random direction, you also have this fixed component that would accelerate the hole in a specific direction, right? You see that at every place that it goes to, there is actually a horizontal displacement, right? Okay. And as a result, right, the sort of final position after this 4 displacement, okay, you find that the position of the hole now shifts, okay, from one place to another. So now there's a net displacement in its location, and this then produces current, okay, because there's a net flow of charge now. So with this presence electric field, right, this basically result in the hole drifting, right? We say that the hole is drifting, and this resulting current is called a drift current. Okay, so the presence of electric field add on to the random thermal motion that creates this drift current. So if we try to do a calculation, right, to analyze the motion of, in this case, the hole in a semiconductor, okay, we can multiply the charge with the electric field that is applied. So the force experienced by the hole will be Q multiplied by psi, the electric field. And, we can also equate that to Newton's second law, Newton's third law, right? F equal ma. And we get, this mass, effective mass of holes multiplied by the acceleration. Okay, so notice that in this case, we use the effective mass because the hole is in an environment, that's influenced by the atoms in the crystal, right? And so this, this interaction with the atoms in the crystal, it's sort of, the effect is basically included in the effective mass, right? And this takes into account the internal forces, so to speak. Okay. So if you do that, we can basically relate the acceleration to, okay, if you rewrite this, okay, we rewrite this expression, then we can actually find out what's the acceleration that the hole is experiencing, right? Which is Q multiplied by the electric field over the effective mass. Okay. Okay. So this actually allows us to try and describe the acceleration that the hole actually experience. Okay. So it's actually related to the electric field that's applied divided by the effective mass of the hole. Okay. Okay, I think just now I might have mentioned something wrongly. This is Newton's second law, it's not third law, by the way. So with this acceleration, right, we can use the equation of motion, right, to describe how the hole actually move, okay, in the semiconductor, using the equation of motion V equal to U plus AT, right, here, where, if you know the initial velocity V naught, the acceleration here is what we have determined here, and multiplied by the time, that is moving, okay? And in fact, with this equation of motion, having the hole sort of moving in the semiconductor, it is, remember, it's this sort of random motion, right? The thermal motion that's also included. We can actually find some average, okay, to this movement, okay, by taking the average on both sides. Okay, if you take the average, which is represented by this bracket here, okay, so if you take the average of the velocity on the left-hand side, okay, you get some average quantity of the velocity in which the hole is moving, and the average of this V0 plus AT, we can split it up to the average of the initial velocity. Acceleration here, it's essentially a constant because the electric field is a constant, right? So we can take that out as a constant, and it's just the average of the time that you can move, right, freely. Okay. So this carriers in the semiconductor, while it's moving in the semiconductor, right, would actually experience what we call collision process with a few things in the semiconductor, right? You could basically collide with the vibrating atoms in your crystal, and at the same time, you also have impurity atoms, right? Your semiconductor could have dopants inside. You can also interact with these impurity atoms. And also the other one is the defects. Okay, if there's defects, then it can also be affected by defects that's present in the semiconductor. So all this can actually causes the carrier to be deflected in a different direction that it's moving. So in general, when you look at a carrier in a semiconductor, right, it doesn't move straight line all the time, right? It doesn't just zip from one end of the semiconductor to the other. Because while it's moving, right, it's going to interact with one of this process, and that will cause it to move in a different direction for a while. Of course, at the same time, the electric field will try and push it in the direction that it's acting. So if you take this into consideration, right, that the carrier actually get knocked around, then you know, when it's moving and it get knocked around, right, it could be knocked around in different directions. So if you consider all the possibility, right, let's say you have, okay, let's say you have a hole, okay, that is initially moving in a certain direction, and then when it interacts with one of this process, okay, it could be scattered in this direction, right, or it could be scattered in another direction here, right, or here. So this process is essentially random, or it could also be scattered in the same direction, right? So depending on how it's scattered, you know, the starting velocity can be a combination of, or can be a variety of all these different possibility in the, you know, different directions. So on average, right, if you take if you take the average of all these different direction, then in fact you can say that the average velocity, starting velocity, will be equal to 0. Okay, because it can be equally likely to be scattered forward, or it can be equally likely to be scattered backward. Okay, so our average of this, it's actually 0, right? So on average, you would have a starting velocity of 0. So we apply this to the average quantity that we mentioned before, right, which is this. Then if you set this to 0, okay, then you just have the velocity being on average equals to acceleration multiplied by some average time that it can move before it get scattered again, or it get kicked in a different direction again. So generally what I can see is that the direction in which the particle is moving, right, is in the net direction of the electric field, you know, but while it's moving, you get kicked in a different direction, then you go again, and then you get kicked in a different direction, then you go again. Okay. So if you actually plot a graph of how this velocity changes with respect to time, okay, so you could get this graph like this. So the directed velocity could sort of increase, right? And then when you encounter a collision, okay, on average, the velocity can be set to 0. And then you sort of be directed in the direction of the electric field again, you accelerate. Then maybe a bit later, then you encounter the collision process, then it's reset to 0. So you get all these different possibilities, okay, depending on how it moves and the chance of it encountering a collision process. Okay, so you get different possible time that you can move freely, right, which is this different quantity here, tau 1, tau 2, tau 3, and so on and so forth. Okay, so the average time that you can move freely, right, this is like a random variable. Okay, it's a random variable with different possibilities here. Okay, it can be sometimes a bit longer, sometimes a bit shorter. So out of these different possibilities, we can actually define average time between collision, right, tau c. Okay, so out of all these different possibilities, right, if you find the average, right, you find the average, and let's say we define this as tau c, we can put it into the expression we have and say that, the average velocity at which the carrier is drifting is just the acceleration multiplied by the average time between collision. Okay, that gives you kind of like an estimate of the average time that, or average speed that the carrier can move in the semiconductor before it undergo a collision process. Okay, that's called the drift velocity. So using the expression that we have sort of determined, okay, by comparing it to Newton's second law, right, and expressing acceleration in terms of electric field and effective mass, and this drift velocity expression, okay, we can write down the drift velocity as q multiplied by the average time between collision divided by the effective mass and multiplied by the electric field. Okay, so we see that the average sort of velocity of movement of your carrier depends on a few things, right? One is the velocity that's applied. Okay, the other is the effective mass of your particle, or the hole in this case, and the average time between collision. Okay, how long before the average time, right, before the carrier undergo a collision and get kicked in a different direction. Okay, so this equation is a useful equation that we can use, right, to work out the drift velocity of your carrier. Now, in this case, you have to take note that this derivation is only applicable for low electric field, where the average time between collision is not affected by the electric field. Okay, at high electric field, you'll find that this average time between collision may change. Then this equation will not be applicable anymore. Okay, so this equation, strictly speaking, is for low electric field regions. All right. So in fact, we can actually lump this together into a single term. Okay, we lump this together and we call this mu n. Okay, the mu n is or mu p in this case, because we're dealing with holes, right? This new mu p. Okay, this mu p is what we call the mobility of the hole. Right? Okay, that's called the mobility of hole, and your drift velocity of the hole is just the product of the mobility with the electric field. Okay, so this mobility quantity is a material property. Okay, you find that in different semiconductor, the mobility will be different, right? And it depends on what material they are looking at. Okay, and the units of the mobility is centimeter square per volt second. Okay, that's the unit, and it basically describes how fast the particle, or how fast the hole in this case, can move given an electric field in the semiconductor. Okay, so the higher the mobility, it can move faster for a given electric field. All right. So similarly, you can derive equivalent expression for electrons, and of course, in the case of electrons, you have to take into account the negative charge. So for the electric force that they experience, it will be minus q multiplied by the electric field, and if you relate that to effective mass of electron multiplied by acceleration, Newton's second law, we can similarly derive an expression describing the drift velocity of electrons. Okay, you notice that the form is very similar to that of holes. Okay, and this q tau cn over mn star, right? This quantity here. Okay, collectively we call this the electron mobility mu n. Okay, and of course in this case we still have a negative sign there, which is not surprising, because in the case of electron, it moves in the opposite direction to electric field, right? So the negative sign accounts for that. Okay, so the mobility term, right, is essentially q multiplied by the average time between collision and divided by the effective mass of the carrier. Okay, so the form is similar to that of holes. So we look at the mobilities of some semiconductor, typical ones like silicon. The mobility of electrons is 1,350. Holes is actually smaller, 480. That means for a given electric field, the electron actually move faster than that of holes. Right? In the case of gallium arsenide, it's even faster. You see that it's like about 8 times faster than that of silicon, and holes it's similar to that of silicon. Okay, so in gallium arsenide, the electron mobility is actually a lot faster, right? So if you need electronics application that requires the carrier to move very fast, so for high-speed application or that, then you would choose to use gallium arsenide because the electron can move faster. So it's good for high-speed applications, right? Germanium is somewhat between silicon and gallium arsenide for electron mobility. Also relatively fast, right, compared to silicon. And in fact, the holes is also quite fast. It's more than that of silicon and gallium arsenide. So these parameters are essentially material dependent. Okay, different materials will have different values for mobilities of electrons and holes. And in fact, although here in the table you see that in general the electrons move faster than that of holes, okay, this is not generally true for all semiconductor. You do find some semiconductor having higher mobility for holes compared to electron. Okay, so it's not necessarily true that electron always move faster. Okay, it could be the other way around in other semiconductor material. All right. Okay, then the next thing is that let's see how mobility is affected by different conditions in the semiconductor, right? So earlier we mentioned about this collision process in the semiconductor, right, that your carrier will experience as it's moving in the semiconductor. One is the thermally vibrating atoms, the host atoms, right? The vibrating atoms will basically provide a resistance to movement of your carrier because they could knock into them, and that will kick them in a different direction. You can also have the ionized impurity atoms, okay, because they have become ionized, right, by giving out an electron or taking in an electron in the vacant bonding. It becomes charged. So when you have a carrier that moves near to it, okay, the charge from this ionized impurity atom can affect its movement as well, okay, as we'll see later on. So this actually results in scattering because the charge will deflect the carrier, okay? And when it deflects, it will move in a different direction, okay? So it's like a collision process. The defect one is, although it's there, it's something that we will not discuss, okay? Because generally in semiconductor that you use, okay, a lot of times the defects are minimized, okay, so that it doesn't affect the material so much. Okay, so although this is one possible consideration if your material is not very good, but in most cases, most application, especially semiconductor material like silicon, okay, the process has been refined so much that usually the defects in silicon it's not so high, that it becomes a concern when you're using it in actual application. Okay, so we will not be discussing the defects effects. Okay, so now all this process that results in collision, the fundamental effect on the carrier is that it actually disrupts the periodic potential that you see in a crystal, right? Okay, in the ideal case, if there's no vibration, if there's no impurity atoms, there's no defects, then the atoms are positioned in well-defined location in a crystal, and the periodic potential that a charge will see is fixed. Okay, it's fixed, right? It's well-defined. Once you have some of this process there, right, for example, the vibrating lattice atoms, then the potential will not be fixed anymore. You'll be changing, right? So that changing periodic potential would manifest in the form of disruption in the potential, and as a carrier moves, this imperfection would cause the carrier to be deflected. Okay, so the same goes for impurity atoms. You get a different charge in the position, right? That will change the shape of the periodic potential. Okay, and that would manifest in the form of disruption in the movement of the carrier. Okay, so all this fundamental effect is that the periodic potential is changed. So let's look at the first effect, which is this lattice vibration due to thermal effect, the vibration of the atoms, right? So this collision process is also known as a scattering process, okay, because it scatters the carrier in a different direction. So for this type of scattering, okay, the thing that we need to understand here is how does it depend on temperature. Okay, that's one of the important things that we want to understand. So in the case of lattice scattering, sometimes also called phonon scattering, because the vibration of the atoms has vibrational energy, right? That in fact is also kind of quantized. Okay, they vibrate in a form of energy that we consider it as like a packet of vibrational energy. Okay, we can treat this as like packet of energy, like photons. Okay, but of course this energy comes from the vibration, so that's why we call this also phonon scattering. So how does it change with temperature? Well, if you think about it, as your temperature increases, okay, you find that the vibration of the atoms become more vigorous, right? And you have a carrier that's moving in a crystal and the vibration is more, then the chance of it encountering the atom and get kicked in a different direction is going to be higher, right? Because if it's vibrating more, then the chance of it encountering the atom is higher, then it's going to be scattered with a higher probability. Okay, so if that's the case, then you'll find that the average time between scattering will basically decrease. Okay, because if the vibration is a lot more, then the chance of it encountering scattering is increased. Then your carrier will not move very far, right, before it encounter a scattering process. Okay, so the average time between collision or average time between scattering would decrease. Okay, it would happen more frequently. Okay, so if tau c decreases, right, tau c decreases from the definition of mobility, right? We know mobility is given by Q tau over effective mass, right? So if your tau decreases, then your mobility actually will decrease as well. All right. So in the case of lattice scattering, if temperature increases, it will actually cause the mobility to drop. Okay, so that's the thing that I need you to understand. Now, what about the case of scattering due to impurity atoms? So in such a process, okay, it's due to the ionized impurity atoms. We call this the ionized impurity scattering. Okay, so the presence of these ionized impurity atoms in the lattice sites, right, will cause this collision process or the scattering process. Okay, so we call this ionized impurity scattering. And if you look at how it depends on impurity carrier concentration, okay, the graph basically shows you how the mobility actually changes with increasing doping for different semiconductor materials. So the horizontal axis refers to the impurity concentration. So you go to the left, okay, the more impurity atoms you put in a semiconductor, right? And you see that the trend is that as you increase the impurity concentration, your mobility actually decreases, right? For both electrons and holes. Okay, and in fact, this is true for all types of semiconductor, right? You look at germanium, if you increase the impurity doping, the mobility actually would decrease. Okay, and this is, again, something that's not surprising, because if you have more impurity atoms, right, in the lattice, then the chance of carrier encountering impurity atoms will also be increased. Okay, because if there's only a little, right, then the carrier will have to move a lot more distance before it encounter one of these ionized impurity atoms. Okay, but if it's more of them, then they'll encounter it more frequently, and the mobility is expected to drop because they get scattered more frequently. Okay, so this behavior is something that you expect. Now, what about the case of temperature? How would the temperature affect ionized impurity scattering? So to understand this, right, you can consider this scenario here. Okay, suppose we have a N-type semiconductor where the majority carrier is actually your electron, right? And in this N-type semiconductor, let's say we have the ionized impurity atom, okay, which is this positive charge that we see there. Okay, so this will be like your ionized phosphorus atom, P+. Okay, because if the phosphorus atom were to give off an electron, become free electron, right? The phosphorus atom loses an electron, it becomes positively charged. Okay, so then let's see how these ionized impurity atoms affect electron that is at different temperature. Okay, so here we are considering say 3 different electron, okay, with different temperature in the semiconductor, right? Where the electron 1 with a temperature of T1 is less than electron 2, which is at a higher temperature T2, and the third one, oh, hang on, this is, okay, sorry, let me repeat that. Okay, in this case, the temperature of electron 1, T1, is more than T2 and more than T3, okay? Okay, so in the case of electron 1 with a higher temperature, right, at a higher temperature, the thermal velocity will be larger as well, right, compared to electron 2, which is at a intermediate temperature. Then electron 3, which is the lowest temperature, you expect electron 3, the thermal velocity to be smaller, okay? So for electron 1, okay, let's say all of them are moving in this direction, right? When they encounter this ionized phosphorus atom, okay, the positive charge would exert an attractive force. Okay, you pull the electron towards it. So in addition to, you know, this velocity that is going right in the horizontal direction, you find that the electron will also experience this attraction force from your ionized dopant. Okay, so there's 2 velocity component now, and the net velocity will be kind of this one, right? It's a vectorial summation of the 2 velocity component, and you find that electron 1 will be kind of deviated from its original path, right? Original path is horizontal, but because of this additional pull from the ionized dopant, you find that electron 1 get deviated, okay, because of this additional velocity component that's added. In the case of electron 2, where the thermal velocity is actually smaller, right? So if you imagine thermal velocity is smaller, so this direction that's going, this vector is smaller, and the pull from the ionized dopant is the same as that of electron 1, then you find that the net force that results, okay, is going to skew it by a larger angle. Okay, it's going to deviate by a larger angle, and you find electron 2 actually deviating more, right? And lastly, in the case of electron 3, okay, the velocity is thermal velocity is even smaller, let's say like that, and then you add this same attraction force from the phosphorus atom, okay, which result in this net velocity that is larger, then you find that the net velocity component, right, it's going to be deviated a lot more from the original horizontal direction. So it could be so much that it could actually cause it to sort of wrap around and get deflected backwards, okay? So in terms of the effect of temperature, right, if you understand this scenario, right, then you can see that when your temperature increases, the thermal velocity, okay, the thermal velocity of your carrier or the electron actually will be larger. So if it's larger, then it's less affected by the ionized atom, okay, because it can move very fast, right? So it moves very fast. This additional pull from the ionized dopant does not deflect the path too much, okay, so it doesn't get scattered so much. So if it doesn't get scattered so much, then maybe it can go straight for a longer period of time, right? And this will imply that the average time between collision can go up, right? Because every time they encounter ionized dopant, it gets scattered a little bit, you know, then every time you encounter, it's just a little bit, right? So you need to actually encounter a lot more, which means it need to travel a longer distance before it get deviated sufficiently. Okay, so on average, the time between collision will increase, and this would then lead to an increase in the mobility. The mobility actually improves with increased temperature in the semiconductor. Okay, so again, this is because your mobility is Q tau over effective mass, right? So if your average time between collision actually increases, then your mobility increases. Okay, so this actually has a opposite effect to lattice scattering, right? If the scattering effect is due to ionized impurity atoms, increasing the temperature actually increases the mobility. Okay, so what that means is that if let's say you have a semiconductor, right, and if you can measure how the mobility changes with increasing temperature, right, you can tell whether it's the dominant scattering mechanism is due to ionized impurity or the lattice scattering. Okay, this actually have opposite effect on the mobility. So of course, in a practical semiconductor, you typically will have these two effects in the semiconductor. The lattice scattering, right, that's always there. That's due to vibration of the atoms, and impurity scattering. Okay, a lot of times you deal with dope materials, right, where there's impurity atoms in the semiconductor. So these two effects are always there, right? Then you find that as you increase the temperature, then it depends on which one is the dominating effect. So if you look at this graph here, it basically kind of illustrates how the mobility changes with respect to temperature and also with respect to impurity dopings. Okay, the graph on the upper part of it, it's actually those with lower doping, right? Remember, the doping itself would decrease the mobility. So if you have lower doping, the mobility actually is higher. Okay, and as you go to higher doping, then you get this scenario where at low temperature, right? At low temperature, as you increase the temperature, you find that the impurity scattering is the dominant component, and as you increase the temperature, your mobility actually goes up. Okay, and once you pass a certain temperature value, okay, around about here, if you keep increasing, the vibration of the host atoms now is so large that it dominates the scattering effect. Okay, and your mobility starts to decrease after that. Okay, and that basically gives you a maximum point for the mobility. If you go to lower doping, like this one here, right? If you go to lower doping, then you find that this maximum point actually shifts towards the left, right? Okay, because the doping is not so high, so as you increase the temperature, it would peak quite quickly. Okay, and then after that, the lattice scattering will dominate and it peaks down. So if you go to even lesser doping, right, then generally you don't see the peak in this graph. Okay, it actually occurs a lot more to the left. Okay, and it just decreases because as temperature increases, it's lattice scattering that's dominating, and you get this decreasing mobility. All right. Okay. So having defined the parameter that describe how the carrier move under the influence of electric field, okay, we are actually now ready to derive the drift current for a semiconductor. Okay, what's the drift current in a semiconductor, right? How do you calculate it? So if you consider a semiconductor, okay, in this case, let's say we have a p-type semiconductor with a whole concentration or whole density of P in the semiconductor. Okay, so remember this is in units of per centimeter cube. Okay, per cubic centimeter. So how many holes are there per unit volume in the semiconductor? Okay, let's say it's P. And let's say there's an electric field, right, such that the holes are moving with a drift velocity of VDP. Okay, that's the average velocity that the hole will be moving. How do we determine the drift current in this semiconductor? So here, let's say we consider a volume element, right, in the semiconductor in the form of a cylinder. Okay. So if you want to find out the current that is flowing in the semiconductor, how do you define current? Okay, current is basically a measure of how much charge passing through some cross-sectional area per unit time. Okay, so suppose in this case, I take this area, cross-sectional area as a reference, let's say area A. Okay, if you can work out how much charge passes through this area in 1 second, then you can find the current, okay, that is flowing in the semiconductor. So the key here is we need to work out how many charge actually flows through this cross-sectional area in 1 second. Okay, right? So how do you find this amount of charge that flows through the area in 1 second? So to find this amount of charge that flows through the area in 1 second, we consider in this case, right, how much of the volume of the charge will flow through this area, right, this cross-sectional area that we are considering. Okay, so in 1 second, right, in 1 second, with a drift velocity of VdP, okay, for a hole, right, a hole will basically travel through a distance of VdP in 1 second. So the amount of charge that will flow through this cross-sectional area will be those within this volume here up to a length of VdP. Okay, so this length here, right, this length here, from here to here, is VdP. Okay, that's VdP multiplied by 1 second. So the charge that will flow through the cross-sectional area A will be all the charge that you find in this volume. Makes sense, right? Because in 1 second, right, the charge that's up to this position will be able to travel to the cross-sectional area and cross it. Okay, anything that's outside this distance of VdP, right, this hole, in 1 second, it will not reach the cross-sectional area. So this guy will not contribute to current. Okay, so within this volume, all right, whatever charge that's in here that crosses the cross-sectional area A would contribute to current. Okay, everybody that's in here that pass through this area will give you current. Now, because we know that the hole density is P, okay, and this is just a volume of a cylinder, so it's cross-sectional area A multiplied by the height, which is VdP, right? That's the volume. And if you know the volume, you multiply with the hole density, then you can calculate what is the total number of holes in this volume. Okay, so that's A multiplied by VdP multiplied by P, right? And so the actual charge amount will be Q multiplied by that quantity. Okay, so the charge that is contained within this volume that will pass through the cross-sectional area is Q multiplied by the hole density multiplied by cross-sectional area multiplied by this VdP, which is the height of your cylinder. Okay, so it's basically these few parts, right? The volume multiplied by the hole density, that tells you how many holes are present in this cylinder that will pass through the area. But to find current, we want to know how many charge, what's the amount of charge that flow through this cross-sectional area. So we have to multiply by Q as well. Okay, so this gives us the total amount of charge that will flow through that cross-sectional area A in 1 second. Okay, that's the amount of charge that will flow through A in 1 second, right? So in fact, if this is the amount of charge, which is Coulomb, that flows through the cross-sectional area in 1 second, then the units for Q is really charge per unit second, right? C per Coulomb per second. And this Coulomb per second is essentially your unit for current. Okay, this is actually your ampere. Okay, 1 ampere is corresponding to 1 Coulomb of charge passing through a cross-sectional area per second. So in fact, this quantity here is current, right? That's actually a current. Okay, so we can write this as the drift current, correct, that is present in the semiconductor with a present electric field, right, is Q multiplied by P multiplied by A multiplied by VdP. So previously, we see that the drift velocity is actually related to the electric field by a mobility term, mu P multiplied by electric field, right? Okay, so we can actually replace this with mobility multiplied by electric field, and at the same time, right? At the same time, this area here, right? This cross-sectional area, we have just taken some arbitrary cross-sectional area. So if you don't know the cross-sectional area, it doesn't matter. We can actually bring the area to the left-hand side so that we get drift current density quantity. Okay, so this drift current density is just the current divided by the area, right? How much current is flowing per unit area. Okay, so if you put in the velocity expression in terms of electric field, right, then you get this drift current density as Q multiplied by P, and then you have a mobility and followed by the electric field. Okay, so we find that the drift current density is a product of the whole concentration with the mobility and the electric field that's present in the semiconductor. Okay, this is called the whole drift current density in the semiconductor. All right. Okay, so in the case of a drift current density, we typically use a J to represent that it's a density component. Now, if you apply this to electrons, right, you carry out the same analysis, you will actually get the same form for the drift current density of electrons, right? The form is in fact quite similar, except that, of course, we replace the P with N, whole concentration, with electron concentration, and the mobility of hole with mobility of electron. Okay, that's the two quantity that replace, but in terms of the form, it's similar, right? Now, the other thing to notice is that in the case of drift current density, you see that the sign is actually positive, right? The sign here is actually positive, and it's basically because the electric field will result in the same conventional current flow, right? In the drift current. Okay, the drift currents are essentially determined by, the electric field. Okay, so your conventional current must be the same. So we can actually think through this, right? If you look at electric field, let's say pointing from left to right, and if you look at the case of a hole, okay, if you have an electric field that go from left to right, the electric force on your hole will be in the same direction as the electric field. Okay, and your conventional current arising from this hole moving left to right is also in the same direction, right? So that's your current that's due to the hole. Now, if you consider a case of electron, okay, electron under electric field actually will cause it to move in opposite direction, right? That's the direction that the electron will be moving. And the resulting conventional current due to electron, right, is actually opposite to electron flow, right? So the electron current is in fact in the same direction as the electric field. Okay, so the electric field will actually result in a current that flows in the same direction as the electric field. Okay, that's why the signs in your drift current equation for both electrons and holes are positive, right? It's positive. So of course, in a typical semiconductor, you have both electrons and holes. And if you want to describe the drift current density, you really have to add up the two, right? So you add up the electron and hole, and you take out the common factor. Okay, you add out two, and you take out a common factor of the electric field. Then you get this quantity in bracket, okay, which we represent as sigma. Okay, this sigma term here is called the conductivity of the semiconductor. Okay, and yeah, so the units of this conductivity is ohm centimeter to power -1, right? So it's per ohm per centimeter. Okay, that's a unit of conductivity. In fact, if you take the reciprocal of the conductivity, you get another parameter called the resistivity, which is the reciprocal of the conductivity term, right? In this case, the resistivity unit is ohm centimeter. Okay, so of course, if you look at extrinsic semiconductor material where the doping is quite large, such that your majority carrier concentration exceeds the minority carrier concentration by a lot, then we can approximate the resistivity or the conductivity to just being dependent on the majority carrier term, right? Okay, so for p-type, then you find that the terms, right, in your expression, only the majority carrier whole term is left. Okay, because if p is much greater than n, then you find that the one of the term become negligible. Okay, that gives you a simpler form. Similarly, if you consider n-type, where electron concentration is much greater, then the whole component actually can be neglected. Okay, then it just depends on the majority carrier type. Okay, so in fact, these are expressions that you're going to use in lab 2, okay, to sort of calculate carrier concentration in a semiconductor. If you can measure the resistivity or the conductivity, okay, that's the equation that actually you'll be using in lab 2. Okay, let's look at an example to derive the relation between voltage and current for a semiconductor using the drift current equation. Okay, so in this case, we have a piece of semiconductor with a length of L, okay, that has a voltage of V that is applied. Okay, so we have a voltage V that is connected to the two ends of the semiconductor. Suppose the cross-sectional area of your semiconductor is A, right, and the resulting current that flows in the circuit is I. So from our calculation, right, we know that the current density is given by the ratio of the current versus the area. So in this case, the J will be I divided by A. Okay, electric field, right, as present, is given by the ratio of the voltage that you apply versus the length of your semiconductor. So it's V over L. Now, so if you use the drift current equation, okay, and apply this to the problem here, so the drift current density is I over A, and the electric field is V over I. And if you rearrange this and express V in terms of I, then you have this term here in bracket, okay, which contains 1 over sigma L over A. So remember, this 1 over sigma is, in fact, your resistivity rho, right? So if you replace that with rho, this is really just the resistance, right, of your semiconductor. So it's rho L over A, which is effectively the same as the equation that you use, right, for resistor, rho L over A. Okay, so this term here is really your resistance R. Okay, so in fact, this drift current density expression, right, it's nothing more than your Ohm's law. Okay, they are actually the same. Okay, this is actually your Ohm's law, which is not surprising because in the case of Ohm's law, it describes the current that you get with applied voltage. In the case of this drift current density, the drift current arises from the presence of electric field, right? So it must be related to Ohm's law as well. Okay, so really the drift current equation, it's actually just the Ohm's law. All right. Okay, so yeah, I think that's all I am going to talk about for today's lessons. Anyone has any questions? No questions? So today's topic actually it's I guess relatively straightforward, right? It's not as demanding as the first few lecture. Any specific questions for anyone? Nothing at all?
Wait, so sorry, could you explain what's periodic potential again?
The periodic potential is essentially this potential that electron or a carrier will see, right, when it moves in the crystal. Remember in the early part, we mentioned that because of this nucleus of the atoms, that is in the lattice position, as your carrier actually move in the crystal, it will see the nucleus effect. Okay, so around each nucleus of the atom, you will experience a potential energy. So if you sum up all this potential energy, you get this periodic potential. Okay, so let me see whether I can pull out the the figure that we talked about previously. Okay. Okay, so this is the one that we are talking about, right? Okay, the carrier electron or hole, when it's moving in the semiconductor, you will see this. You have this potential energy, right, that it experiences due to the presence of atom at each lattice position. So collectively, this is the periodic potential that an electron will experience as it moves in a crystal.
Professor, what lecture notes is this in?
This one?
Yes.
This one is in the part where we talk about the energy band structure of the semiconductor. This is in Appendix D2.
Okay, thank you.
Yeah. So this is in Lecture 2.
Hi,
during-
Prof.
Yeah, during
Right.
Lecture 2. Yeah.
Hi, Prof. Could I clarify which
Uh-huh.
part of the graph is NO/NC exponential, that equation? Like, is it just the bumps?
Oh, okay. Which part is NO?
NC
Oh, the NO
yeah.
expression. Okay. It will be. Okay, give me a minute. Let me find the graph. Okay, you'll be okay. We're talking about just the NO, right? The total.
Yes.
Then it's referring to the area under the curve. If it's NO function, that means NO bracket E, that's the curve. The area under the curve gives us the total electron. So that's N naught. If it's the distribution of electrons at different energy level, that's N naught bracket E.
Oh, I see. Thank you.
And in the case of our consideration, usually we're not interested in, which electron is at what energy level, right? What we are concerned with is how many are in the conduction band. That's why we have to find the area under the curve.
Thank you.
All right. Okay. Any other questions?
Sorry, Professor, can you explain again why resistivity is 1 over the sigma?
Why resistivity is 1 over sigma? That's the definition.
Oh,
Yeah, we quantify that as how well how resistive is a material, and that's related to the inverse of the conductivity. So that's kind of like a defined term.
oh, okay, thank you.
All right. Any other questions?
Professor, so how does the majority and minority carrier concentration, how is it going to be related to our current? Or is there any relationship between the carrier concentration with our current flowing through the semiconductor?
How will the... Sorry, can you repeat again?
How the carrier concentration, what's the relationship between the carrier concentration and the current? Or is there any relationship since...
Carrier concentration and the current. Well, I mean, in the first level approximation, if the current is not very large, right? Typically, we assume that the carrier concentration is the same. It doesn't change.
Oh, okay. I see. Thank you.
Yeah. So in the context of our discussion, typically we just assume that it's a constant. It doesn't get affected. Of course, in reality, if the current becomes very large, then it could actually perturb the carrier concentration in the semiconductor. But I guess in the context of this course, you can just assume that it's approximately the same. It doesn't get affected.
Okay, thank you.
All right. No other questions? Okay, that's good. Okay, if not, just a sort of reminder that next week, okay, we look at your history schedule, right? Next week, it's a 1 week break because of the Chinese New Year, so we decided to put a break there. If not, because of Chinese New Year, some of our classes could get affected. So to make it easy, we just put a break there. Okay, then we'll resume tutorial class in the following week. But take note that in the following week after the Chinese New Year, right? Because Monday is a public holiday for you guys, right? So we have shifted the tutorials. For the Monday one, you come on Tuesday, and for the Tuesday one, we shift it to Wednesday. Okay, please. Wait, no. No, sorry. The Monday one, we shift it to Wednesday, and the Tuesday one remains the same, right? If you look at your schedule. Yeah, correct. Okay. So the Monday class is changed to Wednesday. So please take note of that. Okay, don't come for the wrong class. Because you guys are not supposed to intermingle between the different groups. Okay, so you need to make sure that you stick to your own group. Okay, so next week as a break, we had no class. You don't have to come for class. We resume class on the following week. Okay. Any last question? Okay, if not, yeah, we will stop here for today then. Thank you very much.
Thanks, Prof.
All right.
Okay, thanks,
See you.
Prof.
Thank
Bye.
you, Professor.
All right. Bye.
Thank you.
Prof. Thank you, Professor.
Okay, bye.
Thank you, Professor.
Okay, see you. Enjoy your Chinese New Year.
Oh my God.